So very good morning, one and all. We have learning the subject of your the circuit theory or the network analysis, and the chapter is of a steady state and the transient response. Okay, steady state and the transient response. We have seen what is mean by the steady state condition, what is mean by the transient responses, why we are requiring, why we are studying, what is the need and the purpose of your the steady state as well as the transient response. Few what we can say, we have seen yesterday also the steady state, what we can say, the inductor behavior, uh, as well as we have seen the transient in this transient response, the what we can say in the inductor as well as the capacitor behaviors. Okay, so here today the last is nothing but the steady state capacitor behavior. While we are going to study that capacitor, while the connections are given, while the circuitry is formed, the excitation is given, so what will be the how the capacitor will behave in the steady state condition, that is important here. So what is mentioned here, whenever there is a what we can say the electric circuitry is there and network is formed, and we know very well the capacitor is a storing element. Okay, and in that capacitor, if that is a storing element, the energy which is stored in the capacitor of your the electrical circuitry will be the maximum and the constant if the steady state condition is occurred. There is steady state condition is occurred means what? If the capacitor is in the steady state, it means that there is no flow of a current, or there is no current changes. The current, the value of the current or the flow of the current is not changes with respect to the time period. At this particular moment, the capacitor behaves, yeah, behavior of that capacitor will be the maximum and the constant energy storing element will be treated. Okay, so if we are saying the maximum energy storing, how it is possible to represent in the mathematical form is nothing but my VC is nothing but capacitor energy stored element. This WC, sorry, not VC, WC is nothing but the energy storing element. But why I am written here the C? Just because of the capacitor. So WC is equals to CVC square. Okay, so here just symbolic representation is somewhat different. So you just catch my word, that is C dot V apostrophe S of C square. Okay, VC square by 2. VC square by 2. So how the capacitor stored the energy? WC is equals to CVC square by 2. So in short, whatever the energy stored by that capacitor will be the maximum as well as the constant, just because of the steady state condition. Getting? So VC is nothing but the voltage across the capacitor, which is the maximum. Therefore, at this particular moment, the capacitor is acts as a constant voltage source. So why we are saying the constant voltage source? Because we know very well, if you talk about the current, sorry, inductor, so definitely I am talking about my current. So current will not be changed, or current will be the constant with respect to the time period in the inductor. But whenever we are talking about the capacitor, definitely we are interested to talk about the voltage. Okay, the energy stored in the form of the voltage, you can say, in the capacitor behavior. Okay, so the constant voltage will be there in the steady state condition when we are talking about the capacitor. Okay, while you are going to write the expression for the current, no doubt at all, the current and voltages both will be the present in the inductor and the capacitor. But if you're talking about particularly focusing on the storing element, at that time you should think about the current in the inductor, whereas you should think about the voltage in terms of the capacitor. That I'm telling you. Okay, so next is nothing but how you can write the expression of your current if we are writing for the capacitor specially. So IC is nothing but the current which is flowing through the capacitor. Okay, the current which is flowing through the capacitor is nothing but the IC. IC is equals to C dot DVC. Okay, C, this C is the capacitor dot differential voltage across the capacitor, DVC, divided by dt. And entire term will be at initial condition, or just because of the steady state, it will be 0 ampere. Getting? IC is equals to C dot DVC divided by dt. Getting? So in this way, the capacitor will be act as an open circuited in the steady state, whereas your inductor will be act as a short circuited. Okay. Now come to the next thing. while you are going to study either the steady state or the transient responses, we should know how we can determine the value of your the voltage as well as the current, how you can determine the parameters, that is nothing but voltage and the current. Anyhow, if you are finding the voltage and the current, definitely you will be able to find the power with respect to the T. Okay, getting? So how it is possible? So we should concentrate how we are going to write this term. If you observe this one, this term, this is a sinusoidal waveform, and this term is in the form of you can say the DC form. Okay, this is the in the AC representation phasor diagram. See here, if you observe this phasor diagram, you will be able to find one is directly starting from the zero. This sinusoidal waveform coming down is 0 to pi, and then the 2 pi. Likewise, it will be continuing. But if there is a lagging and leading behavior in the AC fundamentals or AC analysis, okay, at the time this same sinusoidal representation will be either the lead or the lag. Lag means which is the previous one, or the lead which is the further of this sinusoidal. If it's coming from this position to getting back here, that will be lead. This is the previous. Okay, so that's why lead and the lag is totally depend upon whether it's a starting from the before zero or the after zero, or at a particular instant of the zero. Okay, are you getting? So how they are lead, how they are lag. Okay, totally we can represent the leading and the lagging of your the sinusoidal phasor diagram just by writing the voltage and the current equation, standard equation. So see here, plus or minus is totally depend, plus or minus. If you're writing here the plus, or that is a leading, if minus, that is a lagging. And that too, if once waveform is there, definitely one sinusoidal waveform is there, definitely one equation will be there. If you are having a two sinusoidal, definitely two equation. If you are having a three sinusoidal, definitely three equations will be there. And even that equation or expression or the standard equation will be totally depend upon the curve or the graph, how you are going to represent. Just like example, if I'm going to draw the sinusoidal waveform of your voltage versus the time period, getting voltage versus T, or the current versus T. So here, if I'm starting with the voltage versus T, definitely I'm interested to write the equation of a V1, V2, V3 likewise. Okay, and we know very well the standard equation V is equals to Vm sine of omega t, and later on it's totally depend after the omega t, it's a plus or minus of phi. Okay, so leading, lagging, whatever the thing is there. So see here, upper portion will be the plus, bottom portion will be the minus. So this is a plus Vm and minus Vm. Here will be the phasor diagram. That is the difference between the angle is nothing but that 5, and the sinusoidal will be start from the 0 to pi, pi to 2 pi, if that is a particular at a point T. Otherwise, if it will be the 0 minus or 0 plus, depending upon that. Okay, and omega t you can take. Okay, so if you observe this circuitry, you will be able to find again, once again, here the resistor is there, here the capacitor is there, along with your the source. And this source we are interested to write the expression in the form of with respect to the t here. See here, vs of t or a v of t. Simply v is a differ, and v of t is a differ. Simply v is nothing but we are writing the only the source value. But if you are writing with a t, it means that you are interested to write the expression with respect to the time period, that is you are interested in the steady state as well as the transient response. Okay, you are not in the normal mode. We are interested to draw the graph, we are interested to solve the numerical, we are interested to do the mathematical expression, so reduce that circuitry by applying the your differential and the integration form, or you can say in the time and frequency domain, we want to simplify the circuitry. So during that period only, particular period, either the AC or the DC, you can use this T. Okay. Otherwise, simply V will be there, that V is equals to 10 volt. But if you're writing T means the meaning will be changed. Either the time and the frequency domain, we are interested with respect to the time period, all the values. So in this way, how we can apply and what we have learning while you are going to study, while we are going to study the steady state as well as the transient response to find out the voltage and the current with respect to the time period. Similarly, how we can write the expression in that, if the circuitries of AC analysis, and I'm interested to write the expression of AC analysis in the steady state as well as the time domain, that both is possible in the impedance as well as the admittance, because if the circuitry is the series, definitely the impedance will be there, and the circuit is parallel, so definitely the admittance case will be there. If you're talking about the impedance, definitely that denoted by the Z, and we know very well at a resonance, or you can say while you're learning the series circuitry, so Z will be equals to R, and how you can write the expression of a Z in terms of the inductor is there and R is not there, because pure inductor is there, definitely Z will be treated as R will be here 0, so no need to write here the 0, so Z will be equals to J of omega L. Whereas if you want to write simply one source along with your the capacitor, that time Z is equals to 1 by J of omega C. See here in the previous case, if pure R, there is no capacitor here, at that time Z is equals to R. If no R, only the L is there, so that time that Z is equals to J omega L. But if there is no R, there is no inductor, only capacitor is there along with your the source, that time Z is equals to 1 by J of omega C. See here. So these are nothing but in the AC analysis, how we can represent the impedance. That is important. If you're having pure resistor, if you're having a pure inductor, if you're having the pure capacitor in the circuitry along with your the source of excitation. So I can write my impedance in the form of R, in the form of L, in the form of the C. And we know very well, if you're going to write the omega, omega will be 2 pi F. And if we don't have the F, but we are having the T. So that is F is equals to either the 1 by T. If F is given directly, you can find the known parameter of the T also. Now, just come towards the next is nothing but if the parallel circuitry there. And purely R circuitry is connected parallel with your the source of excitation. So definitely my admittance, if these are the vice versa, Z is equals to 1 by Y or Y is equals to 1 by Z. So in this way, the Y will be equals to 1 by R. You can write here the expression Y is equals to 1 by R. Similarly, if I'm interested to find out the admittance, if there is an inductor in the circuitry, okay, so at the time 1 by J of omega L, just because of the parallel circuitry I'm taking here the 1 by J of omega L. Vice versa case of the capacitor, Y is equals to J of omega C, and the omega will be 2 pi F. So in this way we can find easily the for the series circuitry impedances, for the parallel circuitry admittances, to simplify the circuitry for the steady state as well as the transient response. Even we should focus to write the expression of your V of t and the I of t. So see here, if I'm having the sinusoidal waveform or the sinusoidal sinuses, and I want to write the equation or expression in the sine and the cosine function, so definitely that is possible. See here the basic, what we can say, the sinusoidal waveform, we are aware from this figure, that is 0 to pi, pi to 2 pi, 3 pi, 4 pi, like that. And we are plotting this waveform, the voltage versus time, or you can say voltage with respect to the time period. So here will be your V of t, and the maximum peak value wherever you are getting, so that peak value will be the Vm plus or minus Vm. Okay, so likewise if you want to write for the in terms of the time domain, here is the frequency domain. See here omega t, here will be the, because of 2 pi F. Okay, 2 pi F form. Okay, so F will be 1 by T. Okay, so likewise here, in short, you can say this is the frequency domain, but the same thing if you're writing for the time domain, so you can write same, instead of writing the omega t, small t, okay, instead of writing this omega t, you can write directly the t. Okay, you can write directly the t. So here V of t again plus or minus Vm. Okay, plus or minus, because how you will get this t, because omega is equals to 2 pi F, something will be there, P is equal to Vm. Okay, so this omega will be come into the other side, so t will be in the one side only. Likewise you can plot the graph, okay, this waveform. So see here the how you are representing same the frequency domain, this was your the pi to pi, 3 pi, likewise. So you are writing for with respect to the time period, because okay, so t by 2, how you are getting this t by 2t, this is the half, entire cycle is nothing but the completely t. F is equals to 1 by capital T. F is equals to 1 by capital T. So this is nothing but, this is total is nothing but the omega t, or simply the, what we can say, 2, this is the pi, this is the 2 pi. So likewise you can do it directly, that is the omega is nothing but 2 pi F. What is my F? Okay, 2 pi will be as it is. What is my F? So F will be your the either 1 by T, you can write here. Getting? So in this way, this will be the 2 pi 3 t pi t. Likewise, you can convert F is equals to 1 by T, or T is equals to 1 by F. And you should concentrate on the omega also. So in this way, you can do the simplify the expression. But the standard expression with respect to the time period of the voltage, V of t is equals to Vm sine of omega t. Vm is the peak value, okay. So this peak value along with your the sine omega t, omega is nothing but again the 2 pi f, okay. The frequency if you're having, you can write here. And this t will be totally depend upon which sinusoid, at which particular thing you instant you want to calculate. Whether you want to write here, then that will be capital T by 2. If you want to write here, the capital T. If you want to write at this particular instant, this expression, 3t by 2. So at the place of small t, these are the values. Okay. And this phi is nothing but whether it's how much angle leading, lagging, and at particular phasor diagram angle, you can find easily if you're writing for the phi. So in this way, the amplitude or the peak value, if you're the voltages of certain angular frequency in the radians per second, and the phi is nothing but the phasor or the phase angle. Similarly, how I can write the in the transient or the steady state condition for the AC analysis, the imaginary and the real part, how we can plot that one, how we can identify that one, how we can calculate that one, that is too important to reduce the circuitry, to write the expression for that, and to avoid the complexity in the circuit. Everything we are doing the sake of reducing the circuit, avoiding the complexity in the circuit. We are writing the mathematical expression to get what we can say the simplest form of the network. Okay, so all these things matters how we can simplify. So basic fundamental concepts should be clear to write the expression, to know about all these things. Okay, so here also the representation will be in the real, what we can say, the two axes are there. One is the imaginary, other is nothing but the real time. So here the representation will be, if you are starting from the zero, obviously if you are talking about the imaginary, j term will be there. If you are talking about the real, the magnitude will be there. So here 0 plus or minus of a j will be there, and likewise gradually increase the value. Okay, 0 1 1 no need to write, so 1j no need to write, minus 1j no need to write. But if you are going ahead, definitely 2j 3j 4j, here minus 2j minus 3j likewise. And at this particular moment, this will be your magnitude of your the x. Okay, and this is nothing but the your radius. I can take, you can take as a radius, and here will be the other coordinate that is in the vertical form or parallel to this imaginary is nothing but the y. So in short, x and the y are the two coordinates. Okay, if you are talking in terms of the vectors. Okay, so and this is r is nothing but the radius, and this phi is nothing but the angle. Okay, so x, y, z are the three coordinates in the Cartesian coordinate system, or in this z will be treated as your the impedances, and x and y are nothing but the two values in that form of the real as well as the imaginary. So how I can write that this expression, the phasor, this phasor complex representation, how we can reduce this one, how we can represent this one. Okay, so there are a possibility to write the expression is a three-way. That is nothing but you are the, either you can write in the rectangular or the what you can say Cartesian coordinates, that is the real and the imaginary part. See here, so how I can write z is if I'm z is treating as impedances, so z will be equals to real plus imaginary. So real term is on which axis? X axis, and the imaginary is on the y axis. That's why x plus j of y, just like you're the r plus j of x. R will be treated as in terms of the component is a register, whereas X will be treated as a reactances in the imaginary. But if you don't want to talk in terms of the RLC, so at that time, how you can represent your expression? So Z will be impedances, or even you can take the other other value, other coordinate system also. If you don't want to talk in terms of the RLC and the impedance, so at that time that is also possible to write that expression. So the x, y, z are the three components. As a z we can find as the real and the imaginary. How I can write it, the cos and the sine. So this x-axis, this is nothing but the r is the radius. Okay, r is the radius, cos phi plus of j of sine phi. So cos phi is this for the expression of your the x, sine phi is for the expression of your the y. And how you are getting this r is nothing but the resultant one. So we know very well r is equals to root of, here how we can find that radius r is equals to root of this term, that is nothing horizontal term square plus vertical term square, x square plus y square. And what is my x? X is equals to cos of phi. What is my y? Y is equals to sine phi. See here how I can find my x? X is equals to, because at the place of x cos phi, at the place of y sine phi. So B remember x is equals to cos phi, B remember y is equals to sin phi, and the resultant of this one is nothing but the radius. So if you want to calculate in terms of the magnitude, so R will be equals to root of first term square, second term square. And if you want to measure the angle will be tan inverse of second divided by first, yani ki vertical divided by the horizontal term. So likewise in the form of a polar, if you are interested to find the angle, so radius and angle of 5. And if you want to write the exponential form, so impedance will be equals to radius into e raised to the power j5. Okay, j will be the real, what we can say, the imaginary, and the phi is nothing but the angle. Likewise, you can find easily. So how we can simplify the expression if there is a series and the parallel combination is there in the AC analysis? Both the RLCs are connected, the series as well as the parallel. If you are having a cascaded circuitry, if you are having a multi-network circuitry at that time, definitely the many components R, L, and C, they may be connected in series, they may be connected in the parallel. So how we can simplify the expression? So that is possible with the help of the addition, with the help of subtraction, multiplication, division, reciprocal, square root, complex, and the Euler identity is the scientist name Euler. And how we can identify that things in the exponential form that is mentioned here. So if you want to add, okay, so what is the possibility if you are having two things are connected in series? That is nothing but if you're talking about the XYZ, definitely the Z term will be the Z1 and the Z2 if two terms are there. So you can write for the Z1, that is nothing but the X1 plus J of Y1. If you want to write the expression for the Z2, Z2 is equals to X2 plus J Y2. X2 plus J Y2. But if you want to add these two, Z1 and the Z2, at that time, real term will be at one side plus J of imaginary term. Real term, this x1 and x2 are the real term, whereas y1 and y2 are the imaginary. Similarly, the subtraction will happen. But if you want to write the simply directly, what is my z1? So z1 is equals to x1 plus j of y1. z2 is equals to x2 plus j of y2. And do the separation for the addition, that is a real term and the imaginary separate. Similarly, the subtraction, similarly the multiplication. In the multiplication, what will happen? Z1 into Z2, these two terms, so that will be iterated as a R1 into R2, because this R1 and R2 are nothing but the resultant one or the radius one. So you can write that one, and angle will be for the multiplication the phi1 plus phi2, whereas for the division phi1 minus of phi2. Phi1 minus of phi2. In many of this, while we were solving the numerical at the time also, I have explained many times rectangular to polar and polar to rectangular. During that period, we have done these two cases many times. Z1 into Z2, R1 into R2, angle of theta 1 plus theta 2, and Z1 divided by Z2. If division is there, so R1 divided by R2, angle of theta 1 minus phi 1 minus phi 2. Don't go for the notation, but we remember the case what is going on. For the multiplication, angle will be added, and for the division, the angle will be subtracted. Okay, and the radius will be here the multiply, and the radius will be here the divide in the both the cases. If you want to reciprocal, 1 by z will be equals to 1 by r, angle of minus 5. If you want to note down the expression in the square root, so root of z is equals to root of r, angle of 5 by 2. Complex conjugate, if you want to write, that is also possible, that is a z complex. And identity, the exponential form e raised to the power plus or minus j5. And we know very well how we can write this j5, that is a cos phi plus or minus j of sin phi. Cos phi plus or minus j of sin phi. In this way, we can write the expression again in the v of t, vm cos of omega t plus of 5, and what is my v? V is equals to Vm angle of 5 in the phasor diagram. So likewise, we can find easily the amplitude, we can find easily the phase differences, we can find the sine and the cosine functions as, okay, in the time domain. So in this way, the relationship between the integral operation in the form of here the phasor, we can write easily, that is V of t. V of t is equals to V is equals to V. Here, this will be the Vm angle of 5. If you want to note down in the differential form, so definitely with respect to the voltage, that is a dV by dt. dV by dt is nothing but the voltage in the differential form with respect to the time period. At that time, that will be converted either the j omega t, or in short, you can say whenever you are finding the j omega t, and if you want to write the expression in terms of the differential, you can directly take at the place of j omega v dv by dt. Or if you are having a dv by dt, that time you can consider j omega v, vice versa case. Similarly, if integral form is there, the voltage with respect to the time, so integral of v of dt is equals to v by j of omega. So likewise, you can reduce the expression, you can simplify the expression while you are going to simplify the numericals, mini numericals. Similar to that, how I can write, how I should write, what will be my phasor angle, that is too important. So you should concentrate while you are writing the expression of 5. See here, this is the register value, and see here the differences. The plus or minus small v is equals to I current is which is flowing through the R, okay, and we are writing the expression of v is equals to IR. V is equals to IR. So these are the expression in the form of either you can say the real and the imaginary, or the differential form you can say. So if you're writing for the differential, so V is equals to IR. If you're writing for the other case, that time you can do it. So see here. So see here the difference in inductor, small I, capital I, plus or minus V, plus or minus capital V, L. So here small v is equals to L into di by dt. If you are going to write the expression of your the differential form, so voltage voltage across the inductor will be, V is equals to L into di by dt. V is equals to L into di by dt. If you want to write in terms of the what we can say AC analysis, at the time V is equals to j omega L, and L will be L1 and L2 just because of depending upon j omega Li. J omega Li. This is nothing but the current. This is nothing, omega L is nothing but 2 pi FL. Okay, likewise. So if you're writing the work, the current which is flowing across, the current which is flowing through the capacitor, I is equals to C into dV. I is equals to C into dV. I is equals to C into dV. And if you want to measure same thing in the what we can say the current form, so current I is equals to J omega CV. J omega CV. So it's totally depend upon the imaginary term, and the real term is totally depend upon your the differential form. So how we can find again the phasor diagram if you are having the peak value or the amplitude of your the current with respect to your the real time. Okay, so this is the Im is nothing but the imaginary, and R is nothing but the real time. And if we are interested to find out the expression of here the voltage and the current with respect to the phi, so here the imaginary and the real term, we are plotting the graph, and both are in phase. If you are talking about the register, the voltage and the current are in phase. Voltage and the current are in phase, and the angle you can find easily. Similar to that, if you are writing the expression that is a imaginary and the real term, so the current will be lagging. Okay, current will be lag and voltage will be lead in the inductor. See here, voltage will be lead in the inductor, and the current is lagging because this is going from this side, 0, so and so, so and so, so and so, so and so, likewise. And okay, so this is starting from the 0 and going ahead. So here the current which is back, okay, which is lagging, then the voltage. So voltage is leading with the current in the inductor, and this is the we are plotting the curve or the graph between the imaginary and the real term. In this way, you can find easily the omega, angular velocity. Vice versa case in the capacitor. In the capacitor, while you are writing the expression of your the imaginary and the real term, so you will be able to find as the voltage will be the lag and the current will be the lead. Voltage will be the lag, current will be the lead. See here the angle perpendicular to each other, that is a 90 degree. So you, in this way you can find easily the difference between the phasor diagrams. Same thing if you are writing the expression for the impedance and the admittances in the form of the phasor diagram. So the impedance which is denoted by the Z and the admittance is denoted by the Y. So and both are reciprocal or are each other, that is Y is equals to 1 by Z. How I can write in terms of the, how I can write in terms of the current and the voltages, Y is equals to 1 by Z, that is equals to I by V. And this uh, in terms of this Z is equals to ratio of V by I. That is I by V is for the Y, and Z is equals to V by I. Okay, R plus J of X. R plus J of X. That is a resistor and the reactances. Similarly, if you are going to plot, then at the time you should able to think that is X is the reactant, that is the imaginary part you can take, and the R is a real term. See here the periodic function, how you can write V of t is equals to V of t plus N of t, V of t plus N of t, N number of. So t will be equals to, because we know very well omega is equals to 2 pi f. What is my f? 2 pi f. And what is my f? F is equals to 1 by capital T. So what is my capital T? Capital T is equals to 2 pi by omega. That likewise you can write this expression t is equals to 2 pi by omega. Okay, sinusoidal waveform, leading and lagging case, f is equals to 1 by t, omega is equals to 2 pi f. You can write the expression here. So in this way, you can find the expression and the phasor diagram, and you can find easily the periodic functions. Okay. So in this way, I'm going to end this meeting uh, by looking the basic fundamentals related to your the transient response as well as the steady state. In the further lecture, we will continue the transient responses. We will try to simplify by applying the conditions which are related to whenever the switch is closed, whenever the switch, if switch is open, what will happen, and switch is closed, what will happen. So in both the cases, we will apply the conditions. Conditions are nothing but you are at the initial stage, at the final stage, what will be the t is equals to 0, what will be the t is equals to 0 minus, and what will be the t is equals to 0 plus. In all the cases, how we can simplify the numerical on the basis of your the AC analysis, on the basis of your the DC analysis with respect to your the transient responses and the steady state conditions. That is possible. So here up to this, we have studied all the basic concepts. Few are still remain, few parties still remain of a theoretical part related to the transient, that we will see in the next lecture, and we will also try to simplify the numerical on this base, on this chapter. So be regular for the lecture